to you.
Thank you, Amit. I couldn't hear part of the introduction, so but anyway, as Amit was saying, I was doing some condensed matter physics. Then I got interested in glaciers, basically because I wanted to work in landscapes like this. So here, what you're seeing is Hamta Glacier. It's in Himachal. So this is what a typical Himalayan glacier look like. So maybe I thought I'll start with that. So these are the, if you can see my cursor, this white region, that's where the glacier is. That's where the accumulation zone is. That's where this peak is. Basically, via avalanching, it's feeding this glacier, and this ice is moving downhill because of creep of solid. I will come to that in a couple of slides maybe. And then as ice flows down, it also melts because temperatures are higher, melt energy is available, it melts, and you can see the meltwater stream coming out over here. And as you can see, because Himalaya is a young mountain, so it's the surrounding walls are breaking apart and they are throwing a lot of sediments onto the glacier. As a result, the glaciers typically develop a debris cover on the surface. That's why ice is barely visible here. The white stuff that you see here, that's seasonal snow. Okay. Over here, you can see a ice cliff. Okay. But because of the debris and sediment, it looks dark over here. Okay. And this is the glacial stream. And other things that you can notice here is these lines, those are glacial deposits which are marking a old steady state, maybe 150 years back when Earth was colder by a degree. So that's little ice age. Around that time, the glacier would have been over here. Okay, and then the glaciers have been retreating all over the world, most of the places. And I mean that's the thing that I study. But as I'll discuss, that glaciers are, I have already seen that they are contributing to rivers, and we are also seeing signs of a large change in volume. And of course this big storage of water which is reduced to something smaller, this water would have gone and raised the sea level. So glaciers, they contribute to river runoff and sea level. And also, as you were saying, that they are transporting a lot of sediments downstream. So they are basically, it's this glacier that has carved out this wide valley, and it's also eroding at the bottom. So it has a role in shaping the landscapes in Himalaya also. So a glaciologist, any glaciologist to go to field to study these objects uh, would naturally be, doing problems which are relevant to all these issues. So that way, I mostly work on glaciers. I do some field experiments. I try to use some very simple models to bring out some, explain some of the data that we are collecting. And also globally, there is a lot of effort, and particularly in remote sensing, has given us a lot of data to work with. So we are trying to make sense of that change that we have been seeing in the Himalayan glaciers, and what would be the corresponding consequences in river runoff. And we have not really worked on sea level rise, but I'll talk about something. I mean, some of our work has some relevance, so I'll talk about that. And then in the third part of the talk, I'll discuss something that is related to this transport of the debris cover. Basically, we use this some measurement of the flux of debris, supraglacial debris, to find out what is the erosion rate in this, high Himalaya, which is that kind of measurements were there. And then we found something interesting about the Himalayan landscape. Okay, so I'll discuss that. So these are the three parts. So the basic problem that I mean, to summarize, is to understand how Himalayan glaciers, rivers, and landscapes, they're responding to climate forcing. And of course, this is a very broad problem. So there are a lot of different aspects that people are working on. And in this talk, I'll just stick to the work that we have done. So we are only touching upon some aspects of this problem. And with that, I'll start discussing first the response of humans in climate response of glaciers. But just to in the beginning, let me just tell you some some basic introduction to glaciers. So this is a cartoon of a glacier. So these are the higher areas where snow is falling, but it cannot melt because there is not enough energy. The places are too cold, so there is a net accumulation. And lower part of the glacier, there is a net melting, or which is also called ablation. And there is ice flow viscous flow of ice. It's a solid, but it's very close to its melting temperature, so it creeps. And creep of solid is making this flow as a very viscous liquid. The viscosity of ice, effective viscosity, would be something like 10 to the power 15 times more than that of water. So it's really viscous liquid, and the flow rates are something like maybe tens of meters per year to hundreds of meters per year. So that's a very slow flow. And also it's a nonlinear viscous liquid. So the top part of the glacier, it moves more or less like a solid block. That's why glacier surface can crack up. Although it's flowing like a liquid, there are cracks on this, which are known as crevasses, which are related to some of the hazards that you'll have to deal with when you go to field. But anyway, so you have accumulation going on in the upper areas, there is ablation, and glacier flow is trying to maintain a balance, quote unquote, trying to maintain a balance. So if the ablation area is longer, then there is more ablation, so net balance is negative. So glacier area will shrink till it reaches a steady state, and similarly other way around. Okay, so that way if the climate is steady, a glacier will reach a steady state. Also, let me also define this ELA, which I'll maybe refer to a couple of times, which is called equilibrium altitude. So this is the altitude where the net balance is zero, averaged over a year. So whatever I'm talking about here is averaged over a year. Mass balance by definition is averaged over a year. Okay, and this is an altitude because typically energy balance or for example temperature depends on altitude. So that way mass balance is taken to be a elevation dependent function. Okay, and measurements also show that it more or less work well, and it's basically a linear or quadratic curve that works well as a function of elevation. And above ELA it's positive, below ELA it's negative. So as I was discussing, if the climate is steady, there will be a balance between net ablation and net accumulation, and that would define the extent of the glacier. And that's a steady state. And you can convince yourself that that's a steady state, stable steady state. Okay. And now if the climate warms up, that would mean the ELA is going up. So the ablation area is longer. So then there will be a net negative balance, and the glacier will start retreating and try to find the new steady state, which is smaller. And similarly, if the climate is cooling down, then the glaciers will advance. And not only temperature, precipitation will also work in a similar way. And what we are seeing here is a small movie clip which is we are looping over it, and this is shot over by satellites. These are about 11 satellite images taken over 20 years. So, and this extent is about 50 kilometers. This is a particularly large glacier, and K2 would be somewhere here. So this is in Karakoram. Okay, so you can see this very viscous flow because of you can see the supraglacial debris making these streak lines, and as it is flowing down, probably you can see that it's also slowing down, and that's where the glacier ends. And you can see the accumulation zone where the snow, fresh snow is brighter, then it is turning into ice, and these brown areas are the supraglacial debris cover that I was telling you about. And typically you will find a lot of ponds appearing in the ablation zone, which you can see over here. So these are the basic features. And another thing you might have noticed that although there is a lot of fluctuation and a lot of changes are happening over here, like glacier is flowing down, the extent of the glacier is not changing much. And that's because it's a very viscous liquid. So this balance of net accumulation and net ablation is only over decadal time scale. Depends on the response time of the glacier, the size of the glacier, slope, etc. But typically it's at least a few decades or maybe even more. Okay, so as a result, it's responding to only the low frequency climate signal. Okay, so that's why this glacier is steady, and you can probably also see the stream coming out over here. Okay, so also in between, if you have any question, please feel free to stop me. I hope this part is clear to you. Okay.
Argha, I have a question.
Yeah.
The movie you showed is many years, right? This is
yes.
The signal I'm looking at is actually the yearly signal that I'm seeing, this increase, decrease of snow.
Yes, it's not really yearly because we had, in this clip, there is only 11 images over 20 years. So because they were looking for only cloud-free images, and the satellite also takes one image every 15 day or 9 day, whatever. So as a result, there are not too many images. So, but from one summer, typically these will be some summertime images, and 1 year to another, even on the same day, the snow extent would always be fluctuating. So it's a snow extent is a highly fluctuating quantity, and they have plotted only the summer images, end of summer maybe, where the snow extent is the lowest, and cloud-free images. As a result, there are few images. So, but
Sure.
you are getting some glimpse of the interannual variability, because it's a high frequency signal basically.
Got it. Okay.
Is that clear? Yeah.
Yeah. Yeah. Thanks.
Okay. Thank you. Okay, so then simple way to model this would be to just think of a damped harmonic oscillator or a capacitor. So this is the length change signal and depends on the departure from the steady state and any forcing. So old lemons had used this to do some nice analysis that will come to in the next slide. But this is to just to define the response time, because if you just do anyway, and the climate sensitivity. So the C would give you part degree temperature change, what is the length change, and tau would give you the time scale over which this change happens. Okay, and this is just a cartoon I have drawn. So let's say there is a step change in climate, and the glacier length was 3 kilometer. It will now become 2 kilometer because the climate sensitivity of this glacier is 1 kilometer per degree temperature change, and there will be a time scale over which it will attain this new steady state, and you don't care about the small, high frequency fluctuation. So that's all will happen. Okay, so what Oldemans did, he looked at all the records. He did it in 2001. So he had 169 glaciers spread all across the world, for which he had this length change data. So these are, for example, this is Gangotri Glacier. So this line is the length at, this is the zero length line, and zero length for him, and because delta L is measured from with respect to the length at 1950. That's just some convention he has set. And then, so in around 1800, Gangotri Glacier was a kilometer longer, and at present it's a kilometer shorter than whatever it is. So there is overall about 2 kilometer, maybe 2.5 kilometer retreat that has happened. Okay, so he looked at these data sets of all these glaciers, and then he just used them as thermometers, right? Because I've just rewritten the previous linear response formula like this, where on your right hand side you have rate of length change and length. So if you have both, and if you know the climate sensitivity, you can find out what's the temperature change that this glacier is seeing at any instant of time. So he did that analysis. So basically, if it was anyway, so one fine point here that in general this equation would also have a term related to the precipitation change. But Oldemann's argument was ki if I'm looking at a global collection of glacier, then the precipitation changes, they tend to be of random sign, and then they cancel out. Okay, and in the end, temperature signal is all that will survive when you average over a large number of glaciers spread in different geographical locations. Okay, so when he now used this formula together with this 169 records, he obtained this rate curve for the global temperature change, and as you can see, it matches pretty well with the existing estimate of global temperature change over last 500 years or so from all other sources. This blue line is this multi-proxy reconstruction, and the black line is the instrumental record. So you can see that glaciers have recorded a temperature change of about a degree compared to, this is the last little ice age, okay, which was about 150 years back. And that's when I was talking about this Hamta Glacier. Probably it had this longer extent, and since then the glacier mostly have been retreating, but there are of course some regional differences, like this Nigalspin, it was advanced by few kilometers in some time here, right? So there are regional variation, but overall it gives you a good idea of what global temperature is doing. So we had done a similar analysis, collecting a set of glacier data, whatever is available in the Himalaya, and this red line is what we had got, and it also looks similar. About a degree or maybe a bit more temperature rise has happened in the Himalaya. So one point is there that for this we need to know this C and tau for each of the glacier, and they are different for individual glaciers. So what Oldeman did, he modeled a few glacier using a more complicated one-dimensional dynamical model. I'll come to that in a moment. And then he found out some parameterization of this climate sensitivity C and response time tau in terms of the length and slope and other quantities. Okay, so we just had used the same. Okay, so from this match, one would assume that this on the average, his parameterization of C and tau works well, but even the fits that he used that had large error. So for individual glaciers, this kind of parameterization, they don't work so well. So that's one of the problem with this kind of a formulation. Okay. So now, but over, as I was saying, over the last 20 years, we have a lot of remote sensing data. So as a result, we have maps like this available to us. So what you are looking at on the left is, all these circles, they are, the color of the circle is telling us about the mean ice thickness, DHDT is ice thickness elevation change happening over that 1 degree cross 1 degree box. So as you can, and the red is loss and blue is gain. So what we are seeing all across the Himalaya, there is ice loss, or glaciers are thinning down. And interestingly, I mean, and there are some patterns. Like for example, Western Himalaya, it's darker red, and this Eastern Tibet glaciers, they are also losing thinning at faster rate. And very interestingly, glaciers in Karakoram, okay, they are not thinning as much or maybe steady, and glaciers in Kunlunshan and Pamir and all, they are even maybe gaining. Okay, so this is called Karakoram anomaly, which got become a popular topic, because this is, globally glaciers are all doing this, but so it's a mystery like why this is happening. Okay, it's still a mystery. I mean, there are some ideas, so I'll maybe discuss some of those. And this data that we are seeing, that actually the raw data has higher resolution. For example, here it's a very similar data set. I plotted the data for Khumbu Glacier, which is somewhere here. So Mount Everest would be somewhere here. Okay, so this Khumbu Glacier, you can see that very detailed pattern of ice thinning for each of these glacier with a reasonable size. They are available at 30-meter resolution. So there is a lot to explain. And of course, this simple 0D model can tell us something, but there is more that you should be able to, I mean, more to explain basically. So what is going on here, if you want to summarize, one thing is, over this time period, I mean, past few decades, there is meteorological forcing is changing. There must be some changes in temperature, precipitation, snowfall, radiation, incoming radiation, and things like that. So that's the meteorological forcing, and that will also have a pattern. Okay, that would not be spatially homogeneous, I mean, uniform. And then once we have the meteorological forcing, then what you need to do is to fix it, and then that will tell you how much is change in melt, for example, right? So but mass balance, the surface, are you able to hear me? I am hello.
Yeah, we can hear you.
Okay. So I just got a notice that my connection is unstable, so I thought I've lost you. Anyway, so where I was. Okay, so the point is that one need to understand how the meteorological forcing is changing. Then from that, one needs the what is the mass balance change, which is what glacier is seeing. But mass balance, depending on the local climatic setting, I'll come to that in a moment. Or at least one example, it may respond to, let's say, a temperature change in a different way. Okay, for example, depending on whether these glaciers over here, they receive snowfall in summer because they are monsoon fed. On the other hand, these glaciers, they receive their snowfall mostly in the winter through western disturbances coming from the Mediterranean and so on. Okay, so they may have different sensitivities of mass balance. Hello, is there a question?
The climate sensitivity parameter C, can it change science?
Not really, because no. I mean, at least I cannot think of any example where you can do that.
Okay, so they're all, I guess, positive numbers or something.
Yes. I mean, there is a overall negative sign, because if temperature is rising, glacier will shrink.
Right.
So like that. Yeah.
Right. Okay.
And the third point is exactly what I cannot see, but I think it's Vishal, right? So
yeah.
So the glacier response, which is this parameter C and tau. So how they are responding to the mass balance change. So there is three parts to the problem. So I mean, at least tell you something about each of them. So the first thing is the meteorological forcing. It's really uncertain over the Himalaya. So all the data that we have, or maybe the analysis or other things, they are really weak because of the complicated topography that are often not resolved in these low resolution models, and basically you don't have much data here. So weather stations are all, in elevations of maybe 3 to up to maybe 3 kilometer at most. But we are talking about elevation, which is the glaciers are starting at maybe at 4-5 kilometer or 4,000, 5,000 meters, right? So as a result, the climate data is really uncertain. Okay, but overall, whatever climate data is there, and people have done these calculations, because for this you just need to have this climate data, maybe downscale it, and then use the glacier geometry to find out which is the elevation distribution of the glacier surface, to find out, and elevation data is pretty accurate. So find out what is the net balance change given the glacier geometry. Okay, and that more or less matches, but as a consequence of this large uncertainty, I mean, patterns like this Karakoram anomaly, for example, has n number of explanations. Some people have said they are seeing a slight, cooling of the summer. Some people are saying summers are getting more cloudy. As a result, there is a radiative forcing is decreasing. There are other, papers which have suggested that there is, increase in snowfall. But all these, are possible, scenarios, and you cannot distinguish because there is not much data available which will help you to figure out. And most of these paper, to my understanding, they just find out the sign of the changes. Nobody has been able to, for example, quantitatively show that okay, this is this model and I get these numbers which are matching. Okay, so that has not been done to my knowledge. Okay, so that's the problem there. So, and here I don't know, till we have better maybe satellite data of, let's say, snowfall and other things, maybe things will remain like this. Okay, so yeah, so but whatever is available, people have used that, and we have also done something similar. I do not run climate model myself, but I worked with Pankaj Kumar, who is in IISER Bhopal. So they had done a regional climate model and published the results showing their regional climate model analysis, produce the general pattern. As I was telling you, that any reasonable climate data set would produce some of the patterns, like Karakoram anomaly, for example, and they had shown that. So we now then me, Pankaj, and few of my other friends, we sat together and we analyzed Pankaj's data. And what we did, we looked at the sensitivity of the mass balance to various glacier mass balance to various forcing parameters. For example, glacier mass balance would depend on the accumulation, which is snowfall, and then the energy balance terms, which are the short wave and long wave radiation, basically, and the latent heat flux and the sensible heat flux, so the turbulent heat fluxes. And what we saw, that the mass balance variability all over Himalayan Karakoram. So that is roughly 3 watt per meter square according to his model over some 40 years or so. Okay, and these are the quantities that are summing up and giving. Basically, you take a linear combination of these objects to get the mass balance, and this is their variability. And then when we looked at the correlation between mass balance and all these quantities, we realized that mass balance is strongly following the snowfall variability. And but if you look at the snowfall variability, it's probably 4 times smaller than the mass balance variability in terms of absolute magnitude. So there is a strong amplification of the snowfall signal, and the mass balance signal, which is this blue curve over here, over Himalaya Karakoram, averaged over, and these are the annual values over this, about 28 years, I think. Sorry, that's the period over which he had data, simulated data. Yeah.
So the snowfall signal itself will be a function of these radiations and other heat fluxes, right?
Yeah. So there is everything is correlated. And for example, if you have some precipitation, whether that will be snow or not, as you say, depends on for example, you can say at some simple level the temperature at that point of time, right? So that way they are correlated. So but in the end, if we look at the mass balance and the thing that explains it most, that's snowfall. And the basic thing is that these correlations are weaker than this between these two. Okay, and the way to understand this is, one thing is snowfall is contributing to accumulation, and another important role snow cover plays. Snowfall is doing is controlling the albedo. And because albedo, and you can see that the short wave variation is very large, and albedo controls the net short wave, right? So that way snowfall controlling both accumulation and ablation, and at least within that, this model, that's playing a very critical role in determining the net balance. So that was the kind of explanation that we came up, that observation that we came up with. And that's what we think. That's why snowfall would be very, very important for glacier health. But again, the problem is snowfall measurements are very rare, non-existent, and the satellite measurements, they give you a fair idea of the snow cover, but they're not the snow water equivalent. Although maybe in recent few years, maybe some progress is happening. So another important thing we realized, that because the glacier is responding, mass balance is responding to very strongly to snowfall, and snowfall will respond to temperature warming in a different way if the glacier in the snowfall is happening in summer or in winter. For example, in Karakoram, snowfall happens in the winter, and winter is so cold, so maybe 1 or 2 degree temperature rise, it does not really matter, it will still be snow. But on the other hand, in the eastern or central Himalaya, monsoon rain is bringing in and it's causing snowfall, but at much higher temperature. So chances are some of that snow would get converted into rain. So as a result, one would expect glacier mass balance to be more sensitive towards temperature warming in the particularly in the central and eastern Himalaya. On the other hand, in Karakoram, they will be mostly snowfall is not depending on temperature, so warming does not matter as much, and that is kind of consistent with this pattern that we're seeing. So actually, according to Pankaj's model data, both this region and this region, they are seeing similar warming over this 25-year or so period. But these glaciers, their mass balance is not changing because the snowfall does not have any trend here. But in the Himalaya, the snowfall is reducing because of snow is getting converted into rain, and that's at least explain part of this pattern. Of course, it cannot explain positive balance. For that, you need to have either more accumulation or less melting. So there must be more that is going on. For example, one set of maybe couple of papers have recently claimed that the irrigation that is happening in the Indus Valley and also in China in recent past few decades, that has something to do with, that plays a very important role. They say it is the factor that's giving rise to this increased precipitation and snowfall over this region and giving rise to this Karakoram anomaly. So that's again one of the proposals, right? So things are quite complicated, and we are not claiming that we have explained this blue colors, but at least this pattern of low sensitivity to warming can be understood in terms of this summer winter precipitation, summer and winter accumulation in these two regions, and the fact that snowfall is the critical variable as far as glacier mass balance, interannual variability of glacier mass balance is concerned.
Just had one question.
Yeah.
This mass balance curve, there is a dip in around 2000 years. Is it clear why it happens around that time?
Sorry, I have not looked at it in such detail. I won't be able to tell. But it would be either, in simple terms, it would either have been a very warm year or a year where, so that's why snow, or maybe if it is both present in both Karakoram and Himalaya, then these few years snowfall was low. That's also a possibility. Okay.
Okay.
Yeah. So probably, yeah. The dip is there in both. Yeah. Sorry, I'm sorry. Dip is there in both snowfall and mass balance. So within this, data that we're seeing within this model, this mass balance dip is caused by a snowfall dip. Now, the snowfall dip could be due to lower precipitation or precipitation happening during warmer periods. So both can happen. Okay. Sorry, I won't be able to. Did I answer your question?
Yeah, fine.
Thank you so much. Thank you. Okay, so now we'll move to the third part where it's we are trying to understand the glacier dynamics, the glacier flow in explaining and how much to what degree that explains this pattern. I'm sorry, I forgot when did I start. So how much time do I have, Amit? Anyway, so let's continue. So basically, to solve for the glacier dynamics, just look at the mass conservation. H is ice thickness, and ice is taken to be incompressible. So that's ice thickness, and that is changing because this is a 2D model that I have written down over here. That these are the fluxes and the flux divergence term. Due to flow, wherever there is convergence, ice will thicken, and other way around. And this is the mass balance term, which is a function of elevation and also of time. Okay. And of course, this is the forcing, and there are two unknowns, h and the velocities. And velocities can be related to the thickness and surface slope. So the thickness to the power 4 and surface slope to the power 3 within shallow ice approximation of the full nonlinear rheology of ice, which is a Gleim fluid. So ice is basically a shear thinning liquid. The stronger shear, its viscosity reduces. The easier is the flow. And you can take the mass balance function to be linear in elevation. It is kind of matches with what is observed in the field, or maybe a parabolic curve. These are the two commonly used curves. And then once you have the mass balance forcing available to you, and you know the initial thickness and the bedrock, and the surface is just basically the bedrock plus ice thickness, then you can solve this set of equation. As you can see, it's like a diffusion equation, because this is, if you think this is the diffusivity, then this just gives you a 2D diffusive flow. But the diffusion constant is depending on very strongly on h and slope. Okay, particularly h. So it's a nonlinear diffusion problem, but numerically it's not difficult. But the only problem is that you have to solve it at grid size, which is maybe 100 meter, 30 meter, or whatever. But the climate models, they are working on a much coarser grid of 10 kilometer at least. Okay, so that's why so far nobody has worked with coupled models of glacier and climate, or glacier and hydrology. Okay, so that's where the problem is. I mean, technically there is no problem. It's just to do this, you need a lot of computational resources, for example. Okay, so that's why, I mean, more yeah, please.
In the previous one, so till now you have been right in the beginning you showed that all these glaciers are covered by debris,
Yes,
but you didn't
yes,
account for it directly in either the heat flux or this flow or
absolutely not. You are absolutely right. So I am not talking about we have done that, and maybe when I in the end I was going to tell you that I have not done that. But yeah, that's a very important point here, that the debris effect is not included in this model. And but it can be done. I'll tell you about some examples at least, depending on how much time do I have. But yeah, I mean, we are not, that just to keep our life simpler, we are ignoring that for this part of the talk. Okay. And then sorry, my efficient spelling is wrong, but people often because of just numerical complexity, people want a 0D model. And such a model that is very popular is found. I mean, what people do, there is an empirical relationship between ice volume and area, and this gamma turns out to be 1.375, which was derived empirically. Then this bar in their review of geophysics paper is very nicely explained. I'll maybe come to that in a moment. They explain that how it's basically, basically you can do a dimension counting and you can find out this relationship. But it is only going to work on statistically large collection of glaciers where the A is varying over several orders of magnitude, and then the A controls the volume in some way. There are all the other processes, they will give you the scatter, but maybe you can ignore that. But then people, to come up with this model, what they did, you use this and apply it to one glacier, and also ignore C. I mean, assume C to be time independent, which is also not true, and then you come up with something like this. The problem with, I mean, now delta V, the volume change, can be easily computed once you know the geometry and the climate forcing. The main problem is how the glacier geometry changes. For example, how the area changes. So this model, it's just a very simple, estimate of that one can get. And just because of the simplicity, this is what people mostly been using till maybe 2-3 years back. Okay, for example, this is a sea level rise prediction for all from all the mountain glaciers, okay, in the world. So that's what, you know, they are going to contribute about maybe 15 to 20 centimeter depending on the climate scenario. And this is a multi-model average, okay, and maybe at least half of the models, they are based on this very simple method. So what we and I was thinking that I'll tell you about this, how it works, but basically it's very simple. You just count the dimension and that's how it works. And you need to tell and fix the scaling of mass balance with length and width with length, and these are empirically known. So with that, people derive this. And one I mean place where, for example, debris cover shows up is this mass balance scaling exponent m is smaller for debris covered glaciers because of the insulating layer of insulating properties of debris, which reduces the balance ablation rate, which is what Rama was just indicating. So we just did a calculation to show that this exponent is slightly smaller for debris covered glacier, and it matched with Himalayan data, whatever is there. This is not a direct measurement of volume. That's very hard to do. These are some, I mean, rough estimate of volume, but still these differences are showing up. But anyway, just to point, this scaling has various issues which needs to be looked at. But overall, the scaling works and it has been used extensively. Okay, but what has not been done is to somehow that nobody has looked at what is the C and tau that the scaling models imply. Okay, so what we thought that we will look at the response properties within scaling model and then compare with a more detailed research we did, implemented in a computer code, what I just talked about, and then we did it for we ran this model for about 700 all the glaciers in the Himalaya larger than 2 square kilometer or so, which is about 700 glaciers. And this is, for example, Khumbu Glacier as we modeled it. We did not really tune the model, so our glaciers were slightly thicker than they should be, maybe 1.5 times thicker, but overall they were reasonable. Okay, and then what we did, we just applied a step change in ELA and looked at the response of the glacier using both scaling and SIA. And when we did that, we of course now could estimate the response properties numerically. And then we did basically some dimensional arguments. For example, this area change is related to volume change due to the scaling. And what is delta V by V? So this tau is the response time, and beta delta E being the ELA change, is the thinning rate, or the change in ablation rate. And that multiplied by A gives you a measure of delta V, and that when you divide by V, which is H times A, gives you this dimensionless quantity alpha star, and that you expect to control the climate sensitivity. And similarly, tau can be thought of as glacier. This is the typical thickness H of the glacier, mean thickness, divided by the typical melt rate. So BT is the melt rate at the terminus, but glacier, because it has a finite thickness, so its melt rate is not really, and terminus then thickness is 0. So this is the ice elevation feedback, because the glacier is thicker, so melt rate reduces a bit. So this is negative and this is positive, and this ratio gives you a measure of the response time. And we could see that they basically capture some of the variability of response time and sensitivity within scaling models. So this expression, they work well. And a very important point that we could see that this scaling assumptions imply that tau A and tau V, the volume and area response time, they're the same. Okay. Now, when you did the same exercise for SIA glaciers, we got maybe 2 to 3 times larger response time. So the response time is longer, and a very important point was that area response time was slower. Okay, area response is slower, and if area response is slower, then the glacier is spending a longer time in out of balance, because the ablation area is going to remain larger for a longer period. So it's going to lose more ice during this period. So as a result, you expect larger climate sensitivity also, and that's what we see. Okay, if you do this, and then this is maybe something to remember. So for all these Himalayan glaciers, synthetic Himalayan glaciers, so this is the total change for a 50-meter rise in ELA over a few hundred years that scaling model predicts, and this is what you get with SIA. So as you can see, the scaling models are underestimating the total change and also the time over which this change happens, as I just explained, because of smaller response time and smaller climate sensitivity. So possibly this some of these estimates of sea level rise, there is a large underestimation. Okay, we need to really tune the model and see how much and so on, so forth. But overall there is a bias, and we know why the bias is there. So it's going to be there whatever you do. Okay, and this is if because we have this parameterization of the response properties, you can use a Oldman type model, a linear damped harmonic oscillator type response model, and that actually works much better than SIA. But this is also a 0T model, so we just propose that maybe one can use this. But what we have not done is to do it ourselves, and then that requires tuning the model with a lot of data being available about glacier, it's a lot to fit. So we are right now we are thinking how to go about it, whether to do it or not actually. So once we do that, then we should be able to simulate the recent glacier retreat and show how much of it is actually the glacier dynamic signal, and also possibly predict future changes. And these are some just to show some existing predictions. For example, this 1.5 degree global temperature rise, this Paris Agreement. If you look at the RCP models which are consistent with that, they are telling us that Himalayan glaciers or high mountain Asia glaciers, they will lose up from 25 to 50% mass by 2100. So I mean, again, they have used some model there. This is not scaling based model, but some other parameterization, but not dynamic one like SIA. So not, I mean, physically based. It's a parameterization still. So maybe one can compare with these results and see where you can But one point is that much of the variability, for example, they are if you look at all the RCPs, is due to the climate model inputs. That's where the largest uncertainties are. So they are improving the glacier model is, that's why probably not so important, to be honest. Okay, and then include debris effects in this glacier. That's another thing that we did not do yet, but maybe we'll try that. But we have looked at debris effect on mass balance using field experiments and simple models, and we have some interesting results that I'm not discussing today because I'm short in time. And they actually modify the glacier response structure. Clean glacier, just to tell you briefly, would retreat and thin. But in debris covered glaciers, because it takes a long time for the glacier to show any retreat or area change. So area and volume change, they become decoupled. So basically, because now near the terminus, the melt jets are very low. So even if the glacier is out of balance, it cannot remove all that ice very quickly and retreat. So it takes a longer time to retreat. That's what the main change is compared to the clean glaciers. And then problem is more complicated because this debris cover itself is dynamic. And it's very difficult to constrain the parameter, like for example, in-glacial debris concentration. There are hardly any measurement there. Okay, so I'll maybe come to that in the later part of the talk. And there are things like avalanches, which we have worked on, but they are also important because Himalaya has a lot of steep terrains and a lot of avalanching. So these are the complications that one needs to address before we can be confident about these models. Okay, so I'll stop there for the glacier part. So is there any question to previous?
Okay. You mentioned sea level rise many times.
Yes.
So can you tell how important are glaciers as compared to the huge polar sea ice, and as compared to other things like water itself becoming lighter?
Yes. So right now, maybe even 2-3 years back, when I last checked it, so sea level rise rate of sea level rise was maybe 3 millimeter per year. 1 millimeter per year is due to just thermal expansion. Roughly 1 millimeter per year is due to these huge ice sheets, polar ice sheets, and 1 millimeter per year is from glaciers. So they were contributing equally to the other ones, but now over time the other two are taking over, and that's because comparatively the glacier response times are so all these glaciers in the world, they store only 1% of the water. So Antarctic glaciers, they are 100, Antarctica and Greenland, they have probably 90 meter or so water equivalent stored in them, some 80, 90, some such number. But all the glaciers, they are storing only a meter. So of course, over longer time, glaciers contribution would be small, but because their response time is much smaller, right now they are contributing quite a bit. And as you can see, over by 2100, they are expected to be contributing 10, 20, 10, 15 centimeter. Okay, and while the total expected sea level rise is probably about half a meter or so. But again, in Antarctica, there is a lot of uncertainty because there are problems with understanding their dynamics. There could be some very fast modes which have not triggered so far, and people are working on that. There are certain instabilities that people are worried about, where they can suddenly release a lot of water. Okay, but that's what roughly the situation is right now. Did I answer your question?
Yeah, thanks.
Okay. Okay, so now about rivers. So Himalaya and Karakoram, they have a lot of orographic precipitation, and because of high elevation, there is a lot of seasonal snow and glacial ice storage. And the moment you have that, these are slow objects compared to, for example, rainfall. Seasonal snow can store snow maybe, at least few months or maybe even a year or two. And perennial glacial ice, once ice goes into glacier, it can stay there for maybe decades to centuries, right? So they change the nature of the variability over daily to annual to interannual to decadal time scale. Okay, so that's why glaciers are very important. And because of on one hand they are providing water. On the other hand, they are playing a critical role precisely because there is a lot of snow and ice. But again, that's making them vulnerable to climate change, because both these things, they are going to shrink, the snow cover and glacial ice cover, if temperature rise, for example. Okay, but overall, if you look at in the Himalaya Karakoram region, the role of glaciers vary. So for example, in the Indus, which is in the arid region, monsoon does not reach there. So there, this color, this sky blue is glacier, this is snow, and this green is rain, and this is groundwater. And this is the annual hydrograph of rivers in the upper Indus basin, and which is defined by all the region above 2000 meters. Okay, and same here. So this is Koshi, which is a major tributary of Ganga. It's eastern Nepal or something like that. It's that's where it is. And if you now look at Indus, you see a lot of glacier melt is there, and snow melt, and rainfall plays a very small role over there. But on the other hand, in the central Himalaya and places, eastern Himalaya also, because monsoon is such a strong influence there, so most of the water is coming from basically due to monsoon. So clearly, depending on where you are, the role of importance of snow and glacier will change. Okay, so that's something to note. Okay, so other important part that characteristic that a glaciated catchment will have is, let's say here the glaciers are steady and net balance is 0. So at that point of time, there is some melt season runoff, and this is, here we are assuming this region is winter snow fed. Okay, so this is the total runoff, and most of it is summer melt. And now as climate warms up, the glaciers are shrinking, and they are releasing the stored volume. As a result, you get a peak in water. And of course, as the temperature continues to rise, the glacier mass balance is negative. They are releasing excess water that is stored there and becoming smaller. But then they themselves, the storage is also depleting. As a result, after some time, they the peak is again, peak water is reached, and then the runoff decreases. And when the glaciers vanish or they reach some other steady state, you get back to the same runoff. This is the storage loss of the glacier. But the summer season runoff has decreased, because glacier melt was contributing in summer, and winter the glaciers were acting as sink. They are storing the winter snow. That is not happening here anymore. So there is not total, the total runoff does not change if precipitation is not changing, but the seasonality changes. So these are the kind of changes one is expecting. And this peak water maybe is happening sometime close to 2015, some of the central Himalayan river. Those are the estimates. Again, they are very, very uncertain. Okay, so that's another characteristic of glacier is catchment. That's understand. And another very crucial point that was explained in this nature paper is that glacier is the buffer against drought. So look at these circles. So they are various dams and the storage. So these are the areas. In this, for example, this big circle is 15 kilometer cube. Okay. So and in this storage, so this pie chart is the full storage, and these colored ones, they are the glacial contribution. The darker colors are glacial contributions. So as you can see, as we were just discussing, that eastern and central Himalaya, the glacial contribution is not much, and this arid region. So this background shade is precipitation. So these are drier areas. This is wet because of monsoon. So here glacier contribution is smaller, maybe a few percent. But in these dams, on the average, the stored water has 10 to maybe few tens of percent of glacial contribution. Okay, so that's on a average year. But now what Pritchard has done, he has looked at the worst drought in each of these reservoirs over the last 40 years or something like that. Okay, and then he realized that the driest summer month, during that month the glacial contribution really goes up. Okay, so that way during this bad droughts, glaciers are providing water and acting as a buffer against this drought. So that's another very important role that glaciers are playing. And as glaciers shrink, this effect is going to of course go away. So then again how the glacier, that's how the glaciers are going to impact the variability of and extremes of runoff in Himalayan rivers. Okay. Okay, so then we wanted to look at this problem, and again we wanted to look at the sensitivity of the river discharge. So what we did, because I'll maybe be sorry, how much time do I have? Amit, Rama, how much time do I have?
Argha, you can continue like for another 10 minutes.
Okay. So yeah, 10 minutes should be fine. So we looked at the discharge. We modeled the discharge using some hydrological model that will off the shelf, and to look at the interannual variability of discharge and how is it controlled by precipitation and temperature changes. And basically we are looking at the interannual variability is pretty large, and the climate change signal that you are expecting here is comparable to the extreme values that you get in a 20 or 30 year time series. So our idea was to look at the interannual variability of these three quantities and see what is doing what, and extract the sensitivities, just simple using a simple linear regression. And it seems to be working pretty fine. So we are saying that okay, delta Q is depending, which is the discharge change, depends linearly on del P and del T, which are the annual precipitation and summer temperature change. Okay, and delta Q is not the total discharge, is the summer discharge, which is most of the discharge in these basins. Okay, and we have looked at one western Himalayan basin and one central Himalayan basin, and these two are chosen based on their data availability. Okay, and what we see is the precipitation SP, the precipitation sensitivity. If you add maybe 100 millimeter of water, you get 40 millimeter extra discharge. Okay, so there is some storage. Part of it is of course is going to evaporation, but there is also maybe a storage component. On the other hand, 100 millimeter per year is not a very large fluctuation. For example, that defines the range of, if we assume monsoon is 10% variability and 1 meter rainfall, then that's like one standard deviation. Okay, and then if you have 1 degree of temperature change, then you get 3 times more discharge change happen, summer discharge change happening. So these two river basins, Himalayan glaciarized river basins, they are seems like more sensitive to temperature and less sensitive to precipitation, and that's what we wanted to investigate. And that is in line with what Pritchard was saying, like what he was saying, that in the worst summer month on a drought year, there was still some water in these rivers, right? So, and then what we did, because we now have the sensitivities, we can also, because how much temperature change and precipitation change will happen over, let's say 50 years, some estimates are available, and we computed the future changes in river discharge, and using this simple idea, And they kind of matched with whatever other model results were available, which are again more complicated models where they were actually, I mean, computing the glacier evolution, energy balance and water balance as a function of time with some very high resolution grids. So overall, this climate sensitivity seems to be accurate. One extra piece that we had to do to get this match is to realize that this linear sensitivity will only work when you have the background state not changing. But of course, these glaciers over 50 years are going to change by 10-15% the glacier cover. So that's why what we did is instead of looking at the climate sensitivities of the total water, total runoff, total summer runoff, we broke it up into two pieces: the glaciated contribution from glacier part and rest of the catchment. And then we computed these quantities separately, and we said these sensitivities, we assume these sensitivities do not change with time. All that changes with time is this glacier fraction, okay, which can come from another glacier evolution model result, okay. And then you can compute the discharge change. And what was interesting, that when you look at the sensitivities, the precipitation sensitivity of the glaciers, runoff from glaciers, were very low, 10 times lower than rest of the non-glaciarized part of the catchment. On the other hand, the temperature sensitivity was 10 times higher. Okay, so that's another interesting. I mean, it's kind of. I'll come to that. Why is this happening? So basically, what we are seeing is glacier runoff is approximately precipitation independent, and instead of this I mean, basically you can draw up these two terms without losing much on accuracy. So basically, the discharge variability is given by the precipitation sensitivity of discharge of the non-glaciarized part of the catchment times this 1 minus x, where x is the glaciarized fraction. Okay, so now depending on glaciarized fraction, then the precipitation sensitivity of the whole catchment is going to go down. So that's the role glaciers are playing. On the other hand, they are adding a temperature sensitivity to the discharge, and that again depends on the scales with the fractional cover. Okay, glacier cover. And the way this is working, this precipitation insensitive glacier discharge, is because, so for example, these are 2 years. I mean, this is a cartoon model. One happening in winter. So when snowfall is higher, if you look at the snow melt, which is this darker green lines, okay. On a low precipitation year, snow melts. Of course, there is less snowfall, so snow cover, is depleting faster. But then when the snow cover goes away, there is ice to melt, right? So the ice melt starts earlier, and ice can melt a bit more because it's darker, so it because of its lower albedo. So the ice melt is slightly larger, but glacier and snow and I mean on a low precipitation year, the excess melt of ice cover, excess ice melt is going to compensate for the precipitation loss. So basically that's what is going on. So basically the glacier is a reservoir of ice. I mean, some ice, some snow, and as long as you have energy available, it will melt. Whether ice melts or snow melts, it does not really matter so much. Okay, so depending on the melt rates, given the same energy melt rates of ice and snow, there will be some changes in the runoff from glaciers, but not much. So that's what is leading to this almost precipitation independent glacier runoff. Okay, so that's what we are claiming in this paper. It's still under review, and then we can do a few things. I mean, to do things there, we need to do a bit more. I'll talk about something which is again different from this. This is about the landscape evolution. So what we found, some signal of temperature dependent erosion at the top of the Himalaya. Okay, so here again, I'll maybe explain this. Let me see. I think I don't have much time, so maybe I'll another glacier in central Himalaya. This is the glacier from which river Alaknanda is starting from. It's called Satopant Glacier, and this is Mount Chokkhamba. and that's us over here, and this is about 2.5 kilometer tall. So these huge peaks over here, they're all disintegrating, okay, and because of weathering, and all these particles, they are finding their way on top of the glacier. And as you can see, there's hardly any ice. You can see it's under thick debris cover, and some of the big boulders are huge. I mean, there's a huge wide distribution of particles, and all these boulders, they are getting carried downstream, as we had seen in that gif of that animated clip of that Karakoram glacier, right? So what we did, we went to various locations and measured the debris depth, and it varied from tens of few centimeter over here to a meter. So the depth it's increasing because the layers over here, they are slowing down. Okay, the glacier velocity is progressively going down as the ice thins, because it's h to the power 4, right? So as a result, there is some compression and basically a traffic jam. As a result, debris thickens, and also more and more glacial debris is coming to the surface and getting added. Okay, so now that we had this data of glacier ice thickness and also velocities, we could measure the glacier flux. And we had field data from another glacier, Hamda Glacier, the one that I had shown you in the first figure. And we claimed that, we assumed that all the debris that we are seeing, that debris flux is basically getting generated from these ice-free slopes surrounding the glacier area. Okay, and so these darker areas, they are the ones that are producing this debris. So if you know the debris flux and if you know the source area, and we had assumed steady state value, these values did not change much. There are some variation over here due to glacier thinning and slow down, so we ignored those points, and then that gave us an estimate. It's not all the debris flux, because there is a lot of englacial debris. We could not measure that, but we don't think that is going to change the values by order of magnitude. Okay, so now we'll come to the what we in our finding. So we could do this exercise. So this Hamta and Satapant are the glaciers where data, but then similar data existed in derived data, but used all that is there. And then these are the erosion rate values of this Himalayan headwalls. So these are the highest part of the Himalayas. Okay, so that's where the glaciers are starting from. Okay, and this is in log scale, so you can see that it varies from something like 40 meter per million year, so which would be 0.04 millimeter per year to 1 millimeter per year, or 1000 meter per million year. Okay, so these are the typical, these are the spread of rates that we got. And as you can see, there are order of magnitude variability. So even if we make some lot of errors in systematic errors by not including the glacial debris in this, still this variability is very large. So maybe there is some signal. And another important point here is the basin scale, large scale erosion rate measurements, whatever is available in from the lower parts of the Himalaya, looking at fluvial sediments and things like that. And those were much larger. So about at least 2 kilometers per year, or maybe more. Okay, so that is immediately telling us that the crests of the Himalaya, which is the topmost part, is eroding at much slower rate. And that's why that's what we thought, at least one of the ingredient to this fantastic elevation that we have in Himalaya, like almost all the 7,000 meters or above peak is all in the neighborhood of Himalaya, in this high mountain Asia, in around Tibet, like Himalaya, Karakoram, and other mountain ranges. So why this fantastic elevation? So part of the reason would be that as you go to high elevation, the erosion rates seem to be going down. Okay, and they are not much less compared to the basin wide erosion rate, which includes the fluvial parts. Okay, so the question is, what is driving the variability? We tried trial and error, various things that could be potentially be correlated with it, and finally we figured out that it is very strongly depending on the temperature of the head wall. Okay, whatever we could estimate, or the temperature is also related to elevation. So basically, elevation or cooling, the head walls are eroding and less, and the erosion rates are exponentially going down. Okay, Okay, so this was very interesting, because then, as I was describing, that kind of protects the highest peak of Himalaya against erosion, and because the surrounding areas are eroding, so overall the region is getting unloaded. So there will be isostatic response, because the crust is floating, quote unquote, floating on the mantle, right? So it will come up. So this lower erosion is generating both relief and elevation, the erosion and contrast, right? So that way it was kind of interesting. And then why is it happening? And then we realized that this is related to this process of frost cracking, which is a major mode of weathering in these cold landscapes. So basically it's water getting freezing inside the cracks within the rock and expanding and breaking it apart. And this frost cracking intensity, it's most strongest. So these are some experimental results where they hear this frost crack microphone, and from that they can figure out in lab experiments or in field experiments what are the temperatures over which this frost cracking is most efficient. Okay, and based on that there are some models of frost cracking and some simple parameterizations, and you could see that most of this, at least two of these models we tried, and they matched our erosion rates. Okay, so that way we could explain this variability, strong variability with temperature. So one interesting point here, that as the climate is warming up, so this isotherms are moving up, so this frost cracking window is also moving up. So for example, in high Himalaya, you will often find this huge what is called this basically rock falls. Okay, so these have catchments which are higher up, where the rock is splitting because of frost cracking, and this rock debris is coming down regularly. Now this active rock falls, now they are going to shift, because this temperature window over which this frost cracking is working is shifting up. So again, because we have the temperature dependence, how it works, we know the temperature dependence, so it's possible to find out the sensitivity of these rock falls and how their intensity is going to change. We have not done that, but hopefully we'll get down to it and do it sometime. So that way it could be of interest in terms of hazard perspective also. Okay, so I think that's where that's the end of my talk, and I'll be happy to take any questions.
Any questions?
Argha, Vishal here. I just had one question.
Yeah, please.
How do you go about modeling avalanches, since they seem at a completely different time scale than the glacier?
Yeah. So what we did here, so for example, this glacier, you see all these cones that you can see here. So this huge wall that is about 3-4 kilometer wide and 2 kilometer, 2.5 kilometer high, is collecting snow, and because it's so steep, snow cannot stay there, so it's falling down, and these are the areas where you can see avalanching happening. Okay, and what we did, we looked at the mass balance of the glacier over longer time scale, and using that, you are seeing, let's say we define our glacier boundary to be this. Can you see my cursor?
Yeah.
Okay, and then we say, okay, there is some unknown flux coming in here. Okay, it's varying over a very short time scale, but what we are interested in is a long-term average of that. And the glacier dynamics, has this information. If we model the present dynamics without this flux, you will see the glacier would retreat much faster. So we fitted the present retreat and thinning rate for four of the Himalayan glaciers, and that way we constrain this. What is this unknown, missing flux that we are getting, and we could, fix the avalanche. This was probably the only estimate of direct, indirect, but more or less accurate estimate of avalanche contribution to Himalayan glaciers. And you could see that at least 3 of the glaciers where you have mass balance data available, so 90% of the accumulation was happening due to avalanche. And what was happening, because nobody wants to go there, this is very dangerous too, and you cannot do any measurement there. So people were avoiding these areas, and these glacier mass balance were more, reported mass balance, which were measured using, stakes over this region. Okay, so they were much more negative than they actually are because of this missing avalanche contribution. So the measured mass balance and the glacier thinning rate and retreat rate did not match unless we added this big avalanche dam, and the avalanche strength was more than 90% of the total estimation. So it is a huge contribution that was neglected.
What kind of assumptions did you need to make about frequency of avalanches and similar things?
Because this glacier is mainly looking at decadal scale mass balance, right? So
Right.
that's why it does not really matter when this ice is coming down, because that's happening over
I mean,
they are,
I'm saying like number of avalanches per year. Like, do you need to make some assumption on that?
so actually we did not really model the avalanche part. If we want to do, we had plans, because it's possible to measure this cones, their geometries and the avalanche events, because you can hear them very clearly.
Right.
But we had not gone into that detail. What we had identified is a missing flux. So
I
for
see.
that you need not worry about what is, we don't really know what it comes from, and how it comes, and its time dependence and so on and so forth. But what we did over 30-year period,
Can you
yeah, please.
can you say something about frequency of avalanches after having estimated that flux?
No, 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 not really, not really, not really. So what we tried, correlating this precipitation that happens in this region and the avalanche source area, but even that correlation was not great. It did not really tell us anything, because even the precipitation distribution, because of this very complicated topography, is quite different from what you would measure typically in a low lying station, right? So we could not do much. But yeah, you have been thinking about, in particularly this thing you were saying, the distribution of size and frequency, and
Right.
and one thing we planned, that we will install some microphones. So I mean, in number of them, and listen to the sound, and that way at least we know which cone had that avalanche, and maybe also see what is there. But we have not gotten
I
that.
was just thinking if you could use that information sort of to validate your model, or sort of to
Yeah, it
check.
would be very interesting, I mean, something to try, because in the end, when you want to model the changes in the forcing, there you have to from this, how do you translate from climate data to this avalanche feeding,
Right.
right? So in there, this kind of questions we need to be able to address. That's right.
All right. Thanks.
Further questions? Okay, I just want to ask you a last question. It's not directly to do with the science. Like, can you give some idea of what your campaigns are like? Like, you go there and you camp in what kind of weather, and like, what do you eat? And also, what are the things you measure?
Yeah, so we have mostly been going to this Satapant Glacier. Okay, so this is the geometry of the glacier. It's about 10 kilometer long and kilometer wide. These are the typical glaciers that we have been going to, and this is we'll have the glacier terminus would typically be in 4,000 meters. So for a person like me, I have born and grown up in 20-meter elevation, so it gets very difficult. But we have this local villagers, so they help us a lot, and typically we'll be doing two trips to glacier, one before monsoon and one after monsoon. And we have colleagues who are from local universities who go there more often. And the things we have been measuring, for example, in Satpant Glacier, is the mass balance. So all these dots that you are seeing there, we have drilled a hole into the ice and inserted a bamboo stake. And now as the ice surface melts, the stake is coming out, and we know how much is the local melt rate. And also we monitor the stake position, so we know the flow rates. So these are the basic measurement, and also we are measuring the discharge of the river to the extent we can, because the river also, as you would have noticed in that animation, the river also moves around quite a bit. Okay, and the conditions are harsh, but it's very rewarding when you will reach a landscape like that, and so that way it's a lot of fun. and the food is not bad. And in
Basically,
this
you're
high,
saying there are people living there, and you can buy food, you can do all that.
so you can the typically this glacier base camp would be 1 day walk. We choose this accessible glaciers.
Ah,
It will be 1 day walk from the nearest village.
okay.
So for us, it will be one whole day. For the villagers, it will be half a day. So
Right.
we are always, within 1 or 2 days to a village. So we can, anything runs out, we can, you know, get supply. And yeah, so it's not that difficult. The main thing is altitude. That's what makes it very difficult for us. And also these glaciers, because they are debris covered, and it's a big pile of debris. So walking around and navigating through the glacier, that becomes a nightmare. And yeah, so but overall it's a lot of fun.
Okay,
Yeah,
that was a very nice talk. So,
thank you so much.
yeah, thanks so much, Argo. And
And also, I mean, sorry to interrupt you, so also thanks for the opportunity. Nobody is interested in what I do, so I'm really happy that this is probably the second talk in last 1 year that I've given.
okay,
So thank you so much.
for
Yeah,
sure.
Thanks, Argo. Thanks.
thank you, Amit.
Okay, bye.
Okay.